using as an explanation example the device concept discussed in other videos of this channel. Any candidate concept to be useful as a mechanical propellantless thruster has to meet three basic requirements. First, to provide the unbalanced rotation of two interconnected bodies without producing backward forces on the rotation center shaft. Second, be compatible with Newton's third law of motion, which contains the other two laws. Third, to provide a means to explain kinetic energy transfer from the motor to the component to be moved forward. Let's consider a linear electric motor with a rectilinear secondary and a primary containing an extended body, hereinafter called main body, having, in addition, two perpendicular arms extending from the primary housing containing bearings at their ends inserted in a guide on the upper surface of the secondary. When the motor is turned on, a pair of equal and opposite forces act on the primary and the secondary, while the center of mass of the secondary is located in the line of action of the force. The center of mass of the primary is located at a distance from the line of action of the force. The point to note is that, in addition to a rectilinear motion parallel to the applied force, the main body tends to rotate around its center of mass. The inertial resistance of the center of mass of the main body to acceleration causes a torque on the perpendicular arms, which acts on the secondary through the guide walls on its upper surface. Now consider that the secondary is a circular-shaped body, hence with a circular guide on its upper surface, containing internal beams radially extending from a central ring fixed to a vertical shaft, the center of rotation of the system. Since the two bodies are components of an arc electric motor, the intended mode of operation is to rotate the main body inside the fixed angle, stopping and inverting the direction of rotation by means of rebound springs fixed to the extremities of the semicircular body of the secondary, which rotates in opposite direction. At the start of a half cycle, after a momentary stop, the compressed spring starts to expand, applying equal and opposite forces on the bodies. The first effect of these impulsive forces is to set the centers of mass of the two bodies in motion, parallel to the corresponding spring force, as if the center of mass of the main body gains momentum forward and to the right, and the center of mass of the secondary gains momentum backward and to the left. Since the main body starts moving clockwise in the illustration, its perpendicular right arm applies the same force of the expanding spring on the curved outer guide wall of the secondary, with the secondary under the action of an equal and opposite spring force. The curved guide applies a moment on the perpendicular arm of the main body to cause an undesirable anticlockwise twist. In addition to the motion of their centers of mass in a straight line, the two bodies also tend to rotate around their centers of mass, a general plane motion, because the spring forces are applied on the bodies at a distance from their centers of mass. The inertial resistance of the center of mass of the main body at the start of its motion causes a torque on its perpendicular arms, applying an anticlockwise moment on the curved guide of the secondary. Opposite to the anticlockwise moment, the opposite spring force applies on said guide. As a result, the backward motion of the circular secondary body is impeded. Still, during the spring distension, a forward force is applied on the center of mass of the secondary as a forward pull, caused by the tendency of the center of mass of the main body to move in a straight path. This forward force composes on the center of mass of the secondary with the backward force of the spring, producing a resultant force, which causes the rotation of the center of mass of the secondary around the center shaft. This resultant force is tangent to the circular path in which the center of mass of the secondary starts to move. However, the center of mass of the secondary resists this forward motion, and this inertial resistance acts on the center of mass of the main body as a backward centripetal force. This centripetal force composes with the force acting on the center of mass of the main body parallel to the spring force on the primary, producing an inclined backward force to cause the center of mass of the main body to move in this circular clockwise path. In this instant, while the spring is still expanding, the centers of mass of the two bodies start rotating in circular paths around the rotation center shaft. However, as soon as the circular paths are defined, the centers of mass manifest a tendency to move in straight paths in accordance with Newton's first law. These straight paths are asymmetric, and the two centers of mass cannot move along them at the same time. This results in an inertial conflict. To move in its straight path, the center of mass of the main body pulls the secondary body forward, The secondary body manifests inertial resistance and pulls the center of mass of the main body backward. Consequently, the path followed by the center of mass of the main body is a backward curved path between the original straight line and the circular around the center of rotation O. This behavior is in accordance with Newton's third law. It is worth to mention that the forward motion of the system is not due to the two bodies rotating in circles and producing forward centrifugal forces. The tendency of forward motion of the main body along the inclined straight path is defined at the start of the half cycle. Therefore, it pulls the secondary body forward beyond its straight line, defined as a result of the described interactions. The secondary body resists and pulls the main body backward so that it will move in the intermediary backward curved path. It remains to be explained how the main body transfers kinetic energy to the secondary body while pulling it forward. At any point of its path, the center of mass of the main body is under the action of a backward centripetal force, which is the inertial resistance of the secondary body to move forward beyond its own straight path. The centripetal force decomposes into two components, a normal component perpendicular to the tangent to the curved path at that point considered, and a tangential component oriented opposite to the direction of the motion of the main body, that is, a decelerating force. Therefore, the main body decelerates while rotating around the center shaft inside the angle of rotation while pulling the secondary body forward. This process of kinetic energy transferred from the unbalanced rotating body to the non-rotating structure applies to all candidate mechanical and balanced propellantless devices. The present argument implies that the equation force equals mass times the tangential velocity squared divided by the radius of rotation is not the magnitude of the centrifugal force exerted by a body moving in a curved path outward, but the magnitude of the inertial resistance that a first body manifests to move in a curve when connected to a second body. This resistance being applied on the second body that is causing, due to its own inertial resistance to acceleration, the bending of the path of the first body. It can also be considered that, taking the position of the center of rotation at the start of the motion, the radius increases until the end of the half cycle at the opposite side of the rotation angle, resulting in a decrease of the angular momentum. The decrease of kinetic energy of the main body is the amount transferred to the secondary body being pulled forward. If a vehicle structure is added, the backward centripetal force acting on the center of mass of the main body in its rotation in a half cycle represents the sum of the inertial resistances of the secondary body and the vehicle structure to move forward. The shape of the curved path of the center of mass of the main body in each half cycle depends on the moments of inertia of the counter-rotating bodies and the inertia of the vehicle as well as the rotational speed in the half cycle. For instance, the other factors held constant if the rotational speed is low, meaning low operational frequency. The path followed by the center of mass of the main body will be closer to the circular around the rotation center shaft. With an increased rotational speed, the path will be located somewhat farther away from the circle. Increasing even further the rotational speed, the path approaches the straight path which defines the speed limit of the system. The electric motor is turned off during the rebounding process. It is expected that, during the rotations in each half cycle, if the motor is kept running, it will compensate the kinetic energy transfer to maintain the intended rotational speed and, consequently, the operational frequency.